All right, so we are now moving into section 15.5, looking at how to actually calculate equilibrium constants. So just kind of getting right to it. So the best way to probably look at it is to just solve a problem. So here we have an equilibrium problem. Okay, so we have a closed system initially with 1 times 10 to the negative 3 molar hydrogen gas and 2 times 10 to the negative 3 molar iodine gas at 448 degrees Celsius. It's allowed to reach equilibrium, and the analysis of the equilibrium mixture shows that the concentration of HI, or the product, is 1.87 times 10 to the negative 3 molar. Now, we need to calculate the equilibrium constant at 448 degrees Celsius for the reaction taking place. Okay, so this is the reaction on the bottom. It's balanced, okay, so coefficients of 1, 1, and 2. And obviously it's at equilibrium, so your arrow is going in both directions. So how might we go about setting this up? Well, the first thing to think about is to set up a table, and this is called an ICE table. And I would actually kind of modify this if it wasn't, if I actually created these slides. But ICE stands for, so your first row there is the initial concentrations. Your C would stand for change in concentration, and then the bottom row is at equilibrium. What are the concentrations? Okay, so ICE, I-C-E. So you set up an ICE table. Now, and then you put all the entities involved in your reaction. So we have concentration of hydrogen gas, concentration of iodine gas, and concentration of HI. Okay, and so you go to the question and you see that we have initial concentrations for both of our reactants and we have no product to start with. So pretty easy. You just put in those concentrations into the table, and then you obviously have no product to start with, so we have 0. Okay, and then it tells us how much of product we produce or have at equilibrium. So then I can fill that into my equilibrium table right there as 1.87 times 10 to the negative 3. All right, so when we talk about filling in the change, so the change table, well, obviously going from 0 to at equilibrium 1.87, then our change is going to be 1.87 times 10 to the negative 3. Well, if you think of it, so ratio-wise with the balanced chemical equation, for every 1 of the iodine, I produce 2 of the HI. So stoichiometry-wise, then that would mean that I would be removing 0.9 or technically 0.935 times 10 to the negative third moles of this stuff. But obviously I rewrite it in scientific notation so it fits properly. But it's half of what the final product was, because if you think of the balanced chemical equation with coefficients, it was 1 to 2 ratios with the reactant to product. And so we need to half the product to figure out what was the change of the concentration for the H2 and the I2. And so then we complete the column. We kind of change it out. So then we have 6.5 times 10 to the negative fifth and 1.065 times 10 to the negative third. So those are now at equilibrium. I now know the concentrations of my reactants and my products. So I have everything in equilibrium. Well, if I know the concentrations of everything in equilibrium, then if I can write the equilibrium expression, I can plug in the concentrations known at equilibrium and then solve for the equilibrium constant, which is exactly what you're going to do at with your lab that we just did yesterday or today, I guess. So therefore the equilibrium constant, so we take the equation, okay, so remember we use superscripts with the coefficients, and so we get this expression where we've got the products on the top, we've got reactants on the bottom. Okay, and so we plug everything in and solve. Okay, we put in all those concentrations and we solve for K, and K is 51. Okay, so we now know the K. So then let's say, a typical kind of extension of a question like this would be, what is the, what's the product if, or like what would the concentration be of product if these were your starting materials now that you know the K value, right? So applying this scenario a second time, with new concentrations, new starting material, or things like that, since the K is going to be constant. But remember that the K is related to the temperature. So if the temperature changes, all bets are off. All right, so we're going to stop there. So that's kind of, well, that's good enough for right now. And then we'll be getting into what's called the quotient and equilibrium quotient and how it relates to the equilibrium constant. But that will be soon. And with this stuff, I really am sorry that I have not been in the classroom that much. And I know equilibrium is not the easiest stuff to master. So if you would like to come in before or after school to maybe just go over some of this stuff, just do a practice problem or two, and just kind of work at getting a little more confident with this material. I will be available before school tomorrow, as well as I'll be around after school. I have some students coming in, so it would be a great opportunity to take advantage of that. So let me know, and have a good night.